Hello friends, welcome to the Think Pod. Let us discuss here about an important topic of 10th standard, that is real number. In this video, what we are going to learn is about what is Euclid division lemma, Euclid's algorithm and its application. So, Euclid was first Greek mathematician who has written about number theory in his famous book Elements of Geometry. So before going in detail, let's understand few terms like what is called as lemma. So lemma is a proven statement used for proving another statement. This is called as lemma, and about this information was given by Euclid in his book Elements of Geometry. That's why he is called as father of geometry. The second important personality here is Musa al-Khwarizmi. He has given information about what is called as algorithm, which is a series of well-defined steps which gives a procedure for solving a type of problem. So what is a Euclid division lemma? It says, suppose you are having two positive integers a and b, then there exists unique integer q and r which satisfy the condition of a is equal to bq plus r, where value of r is always less than b and more than or equal to 0. We can understand this by taking example of when 58 is divided by 9. Suppose you are dividing 58 by 9. What will happen? You have 58 here, 9 6 ja 54. If you subtract, we can get here 4. So you can see this 58 number can be written as 9 into 6 plus 4, where this 4 is called as what? It is called as remainder. This 4 is remainder of this particular division. So you can see 54 is written as bq plus r. So that's called as Euclid division lemma. Let us discuss few problems to justify the usefulness of Euclid division lemma. For example, the question given is, use Euclid division lemma to show that square of any positive integer, you remember here word square of any positive integer, is either of the form, it can be represented in the form of 3m or it can be represented in the form of 3m plus 1 for some integer m. So what we can say? We can say let a be any positive integer. We can say let a be any positive integer and b is equal to 3. If b is equal to 3, then as per Euclid division lemma, a can be written as 3q plus r, provided your value of r is less than b and more than or equal to 0. So since here value of b is 3, the value of r can be 0 or it can be 1 or it can be 2. That means your a can be represented as 3q or a can be represented as 3q plus 1 or a can be represented as 3q plus 2. These are the three ways by which we can write value of a. But the question is to show that square of any positive integer is square of any positive integer. So we have taken a any positive integer. So we'll take case 1 where your a is equal to 3q, and now square this. A square is equal to 3q square. So we'll get a square is equal to 9q square. Obviously you can take 3 outside, you will get 3q square. Now a square can be written as 3m where value of m is equal to 3q square. We can give it as a point number 1. Then we can take case 2 where we have a is equal to 3q plus 1. So we can take a square is equal to 3q plus 1 whole square. So we can apply here formula of a plus b whole square. That is, we know is equal to a square plus 2ab plus b square. We are going to apply same formula. A square is equal to a square plus 2ab plus b square, that's 1. So a square is equal to 9q square plus 6q plus 1. And you can see here we can take 3 common from this. 3 is equal to 3q square plus 2q plus 1. So a square is equal to 3m plus 1, where value of m is equal to 3q square plus 2q. This is your point number 2. So you can see from point number 1 and point number 2, it is clear. We can say from 1 and 2, square of any positive integer, as it is given in question, square of any positive integer is of the form either 3m or 3m plus 1. So that is the proof. Let's look at next question on the similar pattern. Like suppose question is, use Euclid division lemma to show that the cube of any positive integer. Now here you have a cube. So cube of any positive integer is given by 9m, 9m plus 1 or 9m plus 8. So what we have to say? We have to assume that let a be any positive integer. So what is given? Let a be any positive integer and b is equal to 3. It's a multiple of 9, so we can take 3. So a is equal to b cube plus r, that is what we know. We can write here a is equal to 3q plus r, where the value of r is less than 3 or more than or equal to 0. Okay, so we can take a is equal to 3q, or a is equal to 3q plus 1, or a is equal to 3q plus 2. These 3 value we can take. So let's discuss each case individually. Case 1, when a is equal to 3q. So statement says cube of any positive integer. So I'll make cube of this integer a, that is 3q cube. We will get a cube is equal to 27q cube. A cube is equal to 9. 9 is taken as a common. You will get 3q cube. So a cube is equal to 9m, where m is equal to 3q cube. So a cube is equal to 9m. Take it as a point number 1. That's the case number 1, where I have taken r is equal to 0. Now case 2. Case 2 is when a is equal to 3q plus 1. So now we are taking another case where a is equal to 3q plus 1. Obviously you have to take the cube of this 3q plus 1 raised to cube. Here you have to apply the formula of a cube plus b cube. That is a cube plus b cube plus 3a square b and 3b square a. So a cube is equal to 27q cube plus 27q square plus 9q plus 1. So a cube is equal to, you can see here, we can take 9 common. When you take 9 common, you will get 3q cube plus 3q square plus 1 plus q plus 1. So a cube is equal to 9m plus 1, where m is equal to 3q cube, 3q square plus q. This is the value of m. So a cube is equal to 9m plus 1. Take it as point number second. Now I'll go for third case. That is when you take a is equal to 3q plus 2. So case number 3. A is equal to 3q plus 2. Make cube of this. A cube is equal to 3q plus 2 whole cube. So we will get a cube is equal to is 27q cube, right, plus 54q square plus 36q plus 8, right? That is where we have applied the formula of a plus b whole cube. So we can see here, we can take 9 common. In the bracket, we will get 3q cube plus 6q square plus 4q plus 8. So whatever is in the bracket, take it as a m. So we'll get a cube is equal to 9m plus 8, where your m is equal to 3q cube plus 6q square plus 4q. So we can say a cube is equal to 9m plus 8. So if you compare point number 1, 2 and 3, we can see that the cube of any positive integer is of the form either 9m or 9m plus 1 or 9m plus 8. So we can say from point number 1, 2 and 3, cube of any positive integer, you can write the statement as it is, integer is of the form 9m, 9m plus 1 or 9m plus 8. So we can see here we have followed same statements what we have written earlier, right? You have to assume a be any positive integer, determine the value of b. Based upon value of b, you can select value of r as 0, 1, 2, whatsoever it is required based upon value of b, because your value of r must be always less than value of b. So whatever b you are choosing, based upon that value of r can be selected. Let's look at next question of the similar pattern, where you need to prove that square of any positive integer is of the form of 5q plus 1, 5q plus 4. So you have to represent in this form. So since we have to represent square of any positive integer, we'll take, let n be any positive integer. N be any positive integer. You can take a here also, that's not an issue, you can take any letter. Just you have to write down that given number is a positive integer. And here b is equal to what? B is equal to 5. So your n can be written in the form of 5m or 5m plus 1 or 5m plus 2 or 5m plus 3 or 5m plus 4, because value of r can be 0, 1, 2, 3 and 4, because it has to be less than b. And since here b is equal to 5, so r can be what? 0, 1, 2, 3 and 4. So n can be represented in this form. So we can consider one or two cases to justify the given statement, whether it is represented in the form of 5q plus 1, 5q plus 4 or not. Let's take first example, like n is equal to 5m. If n is equal to 5m, then n square is equal to 25m square, and we can take here 5 constant, 5 outside, we have 5m square, where n square is equal to 5q, where q is equal to 5m square. So you can see here, this is your point number 1. It represents that square of any positive integer is given in the form of 5q plus 1. Now second, If value of n is given by phi m plus 1, then what will happen? Then you can make square of this. You have phi m plus 1 the whole square. You will get n square is equal to 25m square. That's 1. Then you have 10m plus 1. So n square is equal to, take phi common, you have phi m square plus 2 m plus 1. So we have got this. So n square is equal to phi m plus, not m, we can take phi q plus 1, where q is equal to phi m square plus 2m. So you have got n square is equal to phi q plus 1. That is point number 2, where we can see square of any number is given by phi q plus 1. Let's take next example, next case, where n is equal to phi m plus 2. So take n square, we have phi m plus 2 the whole square. You will get n square is equal to, we will be getting 25m square plus 20m plus 8. So we'll get n square is equal to, what we can take it outside, we can bifurcate this. 25m square is equal to 20m. That is one thing. 8 can be written as, I believe, 4 plus 4, right? We can write n as a 4 plus 4. So now what we can say, n square is equal to, we can take, this is a plus b whole square, so we got 25m square, that is 5 2 ja 10 plus 2 times 20m. Then square of this is 4, this is not 8, by mistake it is written, it's a 4, so we'll be having only 4 here, no other, it's not 8, it's a 4. So we can take phi common, phi m square plus 4m plus 4. So we can take this term as a common, n square is equal to phi q plus 4, where value of q is equal to phi m square plus 4m. So what we are getting here, we have got n square is equal to phi q plus 4. So we can see from cases number 1, 2 and 3, case number 1, 2 and 3, we can see that square of any positive integer is given in the form of either phi q, that is point number 1, or phi q plus 1, that is point number 2, and phi q plus 4, that is point number 3. So what we can say here, that from 1, 2 and 3, square of any positive integer is given in the form of, as per given in the statement, phi q plus 1, phi q plus 4 for some integer q. That is the statement. Okay, so we have seen 4 or 5 sums to understand how the Euclid divisor lemma works. The another example we can see in this category is, suppose you have given so that n square minus 1 is divisible by 8. Suppose question is, prove that n square minus 1 is divisible by 8 if n is any odd positive integer. So we can look into that type of question, how it is to be proven. So let's see this. So we have to prove that n square minus 1 is divisible by 8 provided n is an odd positive integer. So we can say that any odd positive integer in the form of 4 cube plus 1 or 4 cube plus 3 for some integer q. For some integer q. So we know since it is divisible by 8, it has to be factor of 8, and since it's an odd positive integer, we must have plus 1 and plus 3 in that, okay, which are odd numbers. So we can take case number 1 where you are taking that n is equal to 4q plus 1. Here n is any odd positive integer. N is any odd positive integer in the form of 4q plus 1 or 4q plus 3. So case number 1, that is n is equal to 4q plus 1. So we can take n square minus 1, that is 4q plus 1 whole square minus 1. We can simplify this. 16q square, 8q plus 1 minus 1. We can say these two will get cancelled. You will get 16q square plus 8q. So we have got n square minus 1 is equal to this. So n square minus 1 is equal to, you can take 8 common, you will get 2q square plus q. So we can see from point number 1, since we have a multiple 8, we can say that from 1 n square minus 1 is divisible by 8. It is divisible by 8. Okay, then we can take case 2. Let's suppose in case 2 we are taking n is equal to 4q plus 3. Now here you are taking n is equal to 4q plus 3. Let's find out n square minus 1. What we will get? It's 4q plus 3 whole square. Then we have minus 1. Make it a plus b whole square. You will be getting 16q square plus 24q. Then we have plus 9 minus 1. So n square minus 1 is equal to 16q square, 24q, plus we have got 8. Again you can see we can take 8 outside. We get 2q square plus 3q plus 1. Now here the multiple is what? 8. So we can say therefore n square minus 1 is divisible by 8. Point number 2. This is point number 1. Okay, so either you say from 1, from 2, we can see that from 1 and 2, what we can see that from 1 and 2, n square minus 1 is divisible by 8. That is what we wanted to prove. Okay, so these are the method and you can say these are the application of Euclid division lemma. Now we can see few application of Euclid algorithm, or you can see Euclid division algorithm, how it is to be used to find out highest common factor of any given two numbers. So Euclid division algorithm, here we are going to learn about how to find out highest common factor of any two positive integer that may be called as a and b, where a is more than b. Very simple steps are to be followed. We have to first decide which number is larger. Take that as a you divide that number with a smaller number, say for example, and you have to keep on dividing that number unless you get your remainder 0. Once you get remainder 0, then whatever term comes in b, that will be called as HCF of number a and b. Okay, so we have to keep on doing that process. For example, if we take 117 and 45, so we can say 117 is obviously more than 45. So 117 is to be divided by 45. So we can see it will go by 2 times. We will get how much? We will get 90, and you have got remainder as a 27. Now you transfer this number to this place. So how you can write this? 117 is equal to 45 into 2 plus what is the remainder? 27. Then this will become your divisor. Here you will get into what? 27. This will come here 27. So 45. Divide 45 with 27. 27 one time it will go 27. 45 minus 27 is equal to 18. So we can write 27 into 1 plus 18. Now again this number will come here. 27 is equal to 18 into. So put 27 at this place. It is one time. So 18 minus how much you will get? You will get 9. So 27 is equal to 18 into 1 plus 9. Then again you can transfer here. You will get 18. 2 times 18 and your remainder comes what? 0. So this will come here. 18 is equal to, and 9 will come at this place. 9 into 2 plus 0. Now since remainder is coming 0, we can say the 9 is the HCF of 117 and 45. So in very simplest form, how we can write it? We can say 117 is equal to 45 into 2 plus what was the remainder? Remainder was 27. So you can take 45 as a dividend. Your divisor comes here. 27 into 1 plus remainder is how much? Remainder is 18. Then we can take 27 here. You will get 18 into 1 plus 9. Then again 18 will come at this place. You have 9 into 2 plus 0. Since your remainder is coming 0, this 9 will be HCF. So HCF of 117, 45 is equal to 9. That is highest common factor which will divide both the numbers. So this is how we can find out HCF of any given number, provided this information is given. Now let's take another example, that is 210 and 55. So we can take this here, that 210, suppose you have 210, you are dividing by 55, obviously it will go how many times? 3 times. You will get 165 minus you will get 45. So we can say 210 is equal to 55 into 3 plus 45. Then 55 will come here and you can write 55 at this place and divide by 45. You will get one time, that is 45. Remainder is how much? Remainder is 10. So we can say 45 into 1 plus 10. So we can take 45 at this place. 45 is equal to, put 45 here. It will go how many times? It will go 4 times. 45, remainder is 5. So we can say 10 into 4, remainder is 5. Then you can take at this 10 at this place. You have 5 into 2 plus 0. That means 10 divided by 5, it will go 2 times. 10, remainder is 0. So once you got remainder 0, we can say HCF is what? 5 is a HCF. So HCF of 210, 55 is equal to 10. So we have got HCF here. It will not 10, it will be 5, because the last we dividing 10 is by 5. So the number is 5. The last example is, that is 237 is more than 81. So if we keep on dividing 237, we can say 237 is equal to 81 into 2 and you get remainder 75. Then 81 is equal to 75 into 1 plus you will get remainder as a 6. Then we can take 75 is equal to 6 into 12 plus 3. Then obviously 6 can be written as 3 into 2 plus 0. Remainder comes 0. So here your last number coming is 3. So you can say HCF of given number 237, 81 is equal to 3. So this is the way we keeps on dividing the given number till you get remainder 0.